So we pretty much finished part A, sketching the Bode plot, and we want to confirm that with this MATLAB version of it. So let's go ahead and try it. The first thing to do, of course, is to get this transfer function into MATLAB in some form. So we'll move over to MATLAB, and I always start out all of my MATLAB scripts with clear and close all, because if I've got figures popping up, it'll get rid of those. So we'll go a little slow on the MATLAB part, but this is also not really a MATLAB class, so yeah, we'll move a little more quickly than if it was a MATLAB class. So we want to define our system. We'll define a variable sys, and we got to put our transfer function into sys. And I've got, let's see, I'll put this over here. We need to transcribe this over to MATLAB. I will move this. Ooh, you're not supposed to see that. Okay. So here's our transfer function. We're going to use the MATLAB function tf to define it, and then I'm gonna use this syntax where I do the ellipsis, and then the next line I'll continue. It's a little clunky in MATLAB to do that, but not too bad. So I need to give it the numerator and the denominator, and so it's expecting an array of coefficients for the numerator polynomial and the denominator polynomial. So the numerator polynomial, I could put 200,000 and then 200,000 as the two coefficients. It's a little bit easier to actually, it's fine to scale a transfer function model object. So I'm just going to say 2e5 times the transfer function object, which is 200,000 times that. Then I can just put in a 1 for the s coefficient and a 1 for the s to the 0 coefficient, the constant in the polynomial. So there's our numerator defined. The second argument is the denominator, which in this case we've got s cubed, so the first coefficient's 1. Second coefficient is 110. The third coefficient is 11,000. And the fourth coefficient is 100,000, so 1e5. And then just for style purposes, we'll close it like this. So actually, I won't put the semicolon, and we'll run this and see what it does. Here is what it returns. It's assigned this continuous time transfer function model. It knows what this is. It's this TF function generates this object that MATLAB recognizes to be a transfer function, and it can do all kinds of things with the transfer function, including simulate the transfer function. If you have a certain input, it'll give you what the output would be, using LSIM or using step or those sorts of functions. But our main concern here is to look at the frequency domain. We want to know what the Bode plot would look like. So put the semicolon there. It's good to just check, oh, does this make sense? This does look like what we put in. So that's good. And one of the nice things that MATLAB can do with one of these objects is make a Bode plot. So it's really just this easy. Bode of sys, so sys is the name of the object that we created, and if we run that, oh yeah, it will, I have to close MATLAB really quick. For whatever reason, if I don't close MATLAB after I plug into the projector, it scales things really weirdly. I don't have any idea why that is. Okay. Here we go. Yeah. Maybe we want to have a grid. So this is hopefully kind of what we sketched, right? So I'm going to move us down to our sketches, and I'll zoom out a little bit so we can see what we sketched next to what MATLAB gave us. Pretty good, right? We got 6 dB. It ramps up at around 10 to the 0. Starts ramping up. We then reduce our ramp, but then we've got this bump. And like I said, in this transition region here, that's the hardest to know because you've got like this second order complex conjugate pole pair that's kicking in from the light blue. And yeah, so that looks pretty good. Our phase sketch is pretty good too, right? Could be a little bit, we were not decreasing quite fast enough. And actually, our problem is that we were following this sort of shape. We also had this green contribution that was decreasing, so we actually should have been decreasing a little faster. But you see that. So, okay, well, we were a little slow on the decrease here, but overall, following the right rough.
Well, it's correct, right? Because that's 10 to the third, now it's 1 10 to the 4th.
Right, and it's pretty, we should be a little further down here. We are still decreasing, but ours is 10 to the 3rd, it goes to here, so we were a little high still, but not terrible. We could have done a little better, but, not bad. All things considered for a sketch, pretty good. That's kind of what we're looking for. And we're trying to think about, okay, this parameter's contribution, this part of the transfer function, how is it contributing? Yeah, approximately we have a pretty good sketch. So that is, it's really easy in MATLAB to come up with a Bode plot. The Bode function actually gives you access to more than just plotting it, though. You can actually get the magnitude and phase information from that if you wanted to. Make your own custom plots and whatnot. So I would encourage you to, in MATLAB, do help or doc Bode and take a look at all of the different options. You can give it the frequencies you want the magnitude and phase at and all kinds of stuff. So, and if you want to plot your own Bode plots, you can get the magnitude and phase values returned to you, and then you can make your own plot with it, which is really nice for making something custom for your homework or whatever. Because the plots that they return to you, you don't have a lot of say in what it looks like. So, they look pretty good. Okay, so that is the first part. So part B, we did. We checked it. Pretty good. Our sketch was pretty good. So then part C, if the input to a system with this transfer function is 5 sine omega t plus pi over 7, so a sinusoid with amplitude 5, angular frequency omega, so that needs to be defined, and then a phase of pi over 7. So that's what the input is. What is the output amplitude and phase for these different frequencies, angular frequencies of a sinusoid? And we could do this by hand. And in fact, let's talk for just a moment what that would look like. What we want to know is what is the output amplitude and phase. We know that I guess I'm using blue. That's fine. Blue's fine. No, it'll bug me if I don't change it to black. It just will. So we've got the output. Oh, I didn't change it. It's okay. I'll live with it. Output amplitude is going to be the input amplitude, 5, times the magnitude of the frequency response function at frequency omega, right? We learned that, I forget what the equation was, but it was one of our boxed equations, right? Put in a sinusoid, you get out a sinusoid. The amplitude changes by a factor of the magnitude of h of j omega, and the phase changes by the phase of h of j omega. So that's our output amplitude. So if we calculate what the magnitude of h of j omega is, which we could find, of course, by just taking our h of s, plugging in s equals j omega, right? So we could say where h of j omega is just equal to h of s, our transfer function, evaluated s equals j omega. So this is the way that we find our frequency response function when we have a transfer function already, right? So we could do that, right? And it's just a number that comes out. It's a complex number that comes out for h of j omega. So we're going to get like 4 plus j 6.2, for instance. And then we have to take the magnitude of it, which is to say we need to take you could use the Pythagorean theorem, yeah, square root of the sum of the squares of the real squared plus imaginary squared, right? So complex plane, real, imaginary, h of j omega is this point. The magnitude is the length of that, and the phase is the angle there. So find magnitude of h. We could do that by hand for those 3 different frequencies, but frankly, it gets kind of messy, right? We don't really want to do it, so that's why we're going to be able to do it by hand for like one case for an exam, right? But you don't want to do it a bunch of times over and over again. And then in the phase, so the output phase, we know to be the input phase, which is pi over 7, plus whatever the phase contribution of the frequency response function is at that frequency. So that's pretty much what C is asking us to compute. But since we're going to have to do this several times, it's really nice to use a built-in MATLAB function called evalfr to do this and not have to go through by hand and calculate what the magnitude and phase of h of j omega are. So let's do that. Let's write us a nice little MATLAB version of this. So the first thing we could say is, let's try out this. I said let's use evalfr. So evalfr, you hand it the system, and you hand it the frequency that you want to be at. So one question is it the frequency, is it the cyclic frequency in hertz, or is it the angular frequency in radians? Let's look. So help evalfr. And it says evaluates frequency response at a single frequency. Evaluates transfer function, the continuous time or discrete time model. Etc. So it doesn't say there, but it says this is a simplified version of frequency response. So maybe the documentation is a little bit more involved there. Yeah. So frequency values should be real and expressed in radians per time unit. So it's the angular frequency that it's looking for. Okay. So evalfr is the function we'll use. So if we wanted to do, for instance, we wanted to know what h of j omega was at, say, an angular frequency of Like, what's one of our break frequencies? Like 1 was one of our break frequencies, right? So we could just plug that in, and if we run our script, I didn't plug in j. It's looking for a complex number. J omega. It's h of j omega, right? We have to plug in the j also. So plug in j times 1, and that gives us a complex number, which is h evaluated at j omega with omega equal to 1 radian per second. So this has a magnitude, square root of the real part squared plus imaginary part squared. And it has a phase if you took the arctangent of imaginary over real. So that's what we're going to do, but we want to do this in a sort of loop where we print out in each case, right? So let's write that. Let's write that inside of a loop. So let's declare an array. Okay, so an omega array. We want them at 1, 10, and 1,000 radians per second, right? So there's an array. We're going to loop through this, and we're going to do this for each case. So let's do a little for loop. We'll start I out at 1. We'll go up to the length of omega a. So we've created I as a sort of index for the loop, right? And each time we go through, we want to compute a couple things, and I think we should just print something. I mean, there's a lot of ways you could do it, but let's just print it out. And there are a lot of ways you could print it out. Let's first compute each thing, and then we'll worry about how to do the print. So the first thing that we want to do is we want to use this evalfr on our sys. We want to evaluate it at j times omega a of I, right? Whatever the current frequency is. So the first time through the loop, it'll take the first value from omega a, and it'll hand it to evalfr. It'll evaluate it, and it'll return to us h of j omega for that omega. Now, I'm not going to actually need to save this because I'm just going to print stuff. So I'll just define that to be something. So let's just call that like h. Okay? Well, maybe h eval. Okay, it's like evaluated at something. H eval. If I want h magnitude, I can use the ABS function in MATLAB, which if you give it a complex number, it returns the magnitude of the complex number. So that'll give me the magnitude. If I want h phase, then there's actually a function called angle in MATLAB that takes the imaginary over the real, the arctan of the imaginary over real. So you can just do angle of h eval. It's sort of a nice little function to have. We could have constructed our own with arctangent if we wanted to, but it's nice to use the built-in stuff. So we've got our h mag, h phase, and we know that our output amplitude is going to be input amplitude times h mag, right? So I'll come up here and I'll define our in amplitude to be 5. We could have just hardwired 5 in, but it's kind of nice to do it a little bit more programmatically so that you have the ability to change it. And the input phase, we'll say, is pi over 7. So our out amplitude is going to equal our in amplitude times 5, right? Or I guess we said 5 times in amplitude. So in amplitude times h mag, yeah. So in amplitude is 5, and then times h mag. Our out phase is going to equal our in phase times h phase. Or plus, right? Plus h phase. You add the phases. So in keeping with these two things that we wrote down, right? So you add the phases, you multiply the amplitudes. And that's pretty much it, right? We didn't really have anything else that we wanted to do. We could do it in dB, but it wouldn't make that much sense. We could look at the HMAG in terms of dB, but since we're doing a multiplication anyways by it, might as well leave it in non-dB units. So let's do some printing then. So each time through the loop, we want to do some sort of printing. And you can use, there are different ways you could do prints in MATLAB. You probably explored a couple of them in your MATLAB class. Sprintf is a nice one because what you can do is you can format the numbers that you plug into them. So you can always do like num to string and then just like make an array of a bunch of strings, and then it just concatenates them, right? Which is totally easy to do, and it's a nice little syntax. But if you want to start changing like how many digits show up in a string, like, or like if you want to be represented as a decimal, a floating point number versus an integer, or how the negative sign appears. There's all kinds of stuff you can change about the number and how it's printed, how many significant figures you want to show. So using sprintf gives you control over that. And so the syntax is, it may be a little weird at first, but what you do is you hand it this long, in some cases, string with little key characters in there that tells it where to put the numbers that you're going to plug into it. And what we're going to do is we're going to make our string actually a concatenation of several lines, because it's a little hard to look at if we write it as one big thing. So we'll put a string here, and then we'll continue it on the next line in a sort of concatenation. So another thing there, and then finally at the end we'll close it. And then you hand sprintf your numbers. So yeah. So then you hand it your numbers. So in this case, we're going to need to put in several things. Like for instance, in amplitude might be a number we want to give it. And then we'll end it. And you can't, I don't think you can put a semicolon, or it suppresses the output. So let's actually try this. So like percent 0.5, I think gives us 5 significant figures G for a floating point number, as I recall. I needed my ellipses there. So I think this won't give us any syntax errors. Aha! Great. So in amplitude got inserted there at this format specifier. Okay? So that was the sort of syntax. And now that we're comfortable with that, we can go in and put our more complex stuff that we want to print out in there. So I'm going to say for input amplitude, and I'm going to put in my in amplitude. So this just goes in order. So in amp is the first one. And then I'm going to say new line. So when it prints out, it'll give me a new line. And input phase. Well, first off, probably the frequency is the most important, right? So maybe I should do that one first. So maybe for input, or for input frequency, so we'll put omega A of I is the input frequency that we're currently on in the loop. And so input frequency, this, and input amplitude this, and input phase this. So then let's just check this so far to see how we're doing. So for input frequency 1000, input amplitude 5, and input phase this. So I probably wanted a new line there. Input phase this. So now I've got a new line showing up there. The output, I guess I could say H magnitude is, so I want to give it H magnitude. So this is our H mag. And then I'm going to do phase too, right? H phase. Magnitude is this. Phase is that. I'm missing some new lines in there. And then let's and the output amplitude is, so we need to put output amplitude in. So out amp, that's what I called it. And then we're also going to do out phase, right? Okay, output amplitude is that. Almost there. Oops. And the output phase is that. Oops. Okay. See if it works. Sweet. Hopefully I did it right. It runs. So the first time through, it says for input frequency 1, so angular frequency, right? Probably should say that, but and input amplitude 5, and input phase pi over 7 is apparently 0.4488 radians. H magnitude is 2.8145. So that means that we are going to be multiplying this input amplitude of 5 by 2.8145. And the phase is 0.6573, meaning we're going to add this phase to the input phase. And so at the output, we get 14.073, which is 5 times 2.8145. I just believe it's true. And the phase is 0.488 plus 0.67573, which is 1.1245. So that was for the first frequency. So for the next time around the loop, input frequency is 10, input amplitude is 5, H magnitude is 14.2. So we're going to multiply this 5 by 14.2. So the output amplitude is much larger than the input amplitude in this case, 71 instead of 5. And the phase also has a different contribution. And finally, we've got our input frequency of 1,000, so getting up to high frequency. So we should be able to get a sense of this when we look at our sketches, right, or our Bode plots. So out here at 1,000, we're expecting that the magnitude in dB is, we're multiplying by a number that's smaller than 1. So we're going to get smaller than the input amplitude. When we're down here at 2 10, or what was, yeah, the last one was 10, right? Down here at 10, the output amplitude is larger than the input amplitude. So dB plus 23 dB. So it's a pretty significant gain. Out here at 1,000, we're going to be multiplying it by negative 14 dB, or negative 14 dB converted to an amplitude. So that should be coming out smaller than the input, and it is. So input was 5, the output is 1, amplitude-wise. And then the phase contribution is much more negative, and we see that show up also in the output phase. So that, I mean, we did that. We kind of see that there's this frequency response, right? So if you put in a sinusoid down here, we're doing one thing to it, right? It's the output amplitude is coming out to be a little bit more than the input amplitude. Out here, output amplitude is coming out to be a lot higher. So if you're in some intermediate range in your input frequencies, you're going to see this big amplification. But when you get to higher frequencies, you're going to see this attenuation of your input. So usually the amplitude is more interesting than the phase, just because amplitude is related to the energy in the signal. And so usually the energy in the signal is something that's physically kind of interesting to us, right? The power of the signal. So if it's like an audio signal, then this is how loud it would be. Whereas the phase would mean like this is the maybe related to like a time lag, for instance, in an audio application. So you can get phase distortion and all that. There's all kinds of interesting stuff to do with the phase. And so for an amplifier that has a phase profile that looks like this, where this big shift happens is really important, because if you've got acoustic sounds that you can hear coming through your audio signal that are across this, it's going to end up with a lot of distortion. If you're in a flat region, so if all of your acoustic stuff happens up here, you're fine because it's flat. The phase is flat up there. But so amplifiers, this is one of the things we care often a lot about, the volume or the magnitude of the signal, what the output amplitude is. But the phase can be a really important thing to worry about. And so those of you who are in my instrumentation class, you know that the phase distortion is something we talked about in that class. But it's something that I hope to have time to talk about next week, but with the exam and everything, I don't know if I'll be able to. In any case, this is a way to visualize the frequency response of the system and kind of characterize how it responds to sinusoidal inputs at different frequencies. So, any questions? Yeah.
With the originally when you're writing down the notes, you supposed that the transfer function was 5 sine WT plus pi 7, correct? Yeah.
So this was the input.
Yeah, okay, so with the output amplitude, is that 5 times the magnitude of HJW?
Exactly.
Or is that the input amplitude?
So this is the input amplitude, 5.
Got it.
And so in order to get the output amplitude, we need to multiply that by the magnitude of H of J omega.
Okay, which is the output, okay.
Yeah, which gives us the output.
And then the output phase is equal to the input phase, which is pi over 7 plus HJW, right?
Exactly. And there's a I don't remember what the equation number was that we gave it, but it's the boxed equation we had a couple lectures ago. I think it was 6.4 that had for an input sinusoid, what is the output in steady state, or what is the forced response? And we did a derivation using Fourier transforms to find this relationship. So it's a pretty cool one. So the output amplitude is just the input amplitude times the magnitude of the frequency response function. The output phase is just the input phase plus the frequency response function phase. So yeah. And MATLAB, you're starting to see why people use MATLAB to do this sort of analysis, because I will say Python's getting a lot better with this too. You can do similar things to what we're doing here in Python. But instead of having to write a mathematical function to do things, even as simple as what we did here when we found the angle and the absolute value, we could have written a little script that takes the real part and it squares it, and we could have taken the arctangent. We could have done those things, but MATLAB has a lot of stuff built in that's nice. And in particular, this Bode saved us quite a bit of work because we would have had to define the transfer function in another. So having this TF defining the transfer function and having Bode of that give us what we want is really nice. We would have had to actually work, define a MATLAB function that's a complex value function. We would have to plug in these complex values into it, evaluate them at each point, return it in a logarithmic scale, and plot it, which isn't that bad, but it's definitely a lot of work. So when you have these sorts of tools at your disposal, it makes it pretty nice. So it's worth learning the MATLAB tools. And I would say that we learn how to sketch them because we want to gain intuition about them and how if we were to change a system by multiplying it by this transfer function, and we will do that in a couple weeks, that's how our controllers are going to work. When we start doing feedback control, we're going to have a transfer function that we get to multiply by a transfer function that we can tune. So that's our controller. And we want to know what multiplying that one transfer function by another one that we are interested to control with, how that affects how the system behaves. And having a little bit of intuition from the Bode plots and knowing how to sketch them will help us to do that. So, yeah. So it's really useful, but if you really want a nice Bode plot, it's really easy to do. So I encourage you when you're studying to know how to sketch them, but it's a great way. You can just arbitrarily make up a transfer function if you want to. Try to sketch it, and you can check what the right answer is in MATLAB with 5 lines of code. So it's not bad. I think in the notes, so I put the code in the notes. There's a line that was up here that was like a hanging chat of a line that I didn't use. So you can cross that out. I think I called it omega. That's deprecated now. And then I wrote out the loop and everything. So I think that everything that we did in class is in these code listings, MATLAB code listings. So you should be able to just copy and paste them and they should work. Give you a place to start when you're doing this for yourself. So, all right, any other questions? Okay. Yeah. Good luck studying.